Okay, so what we're going to do today is to finally leave the assumptions of completely eviscid flow, and we'll discuss for the first time a solution which does involve the viscous term in the Navier-Stokes equation. So we'll discuss boundary layers. Okay, so that we'll start with a brief introduction. And so we'll just start with reminding ourselves of the momentum equation. So here is our momentum equation. The inertial term on the left-hand side, which comes just from the mass times acceleration term for a continuum. So rho partial u partial t plus u grad u. Right, so two things when you see this equation. First of all, it's a statement of Newton's second law, and so remember this is a vector equation. Okay, you have several components. So the inertial term is equal to the sum of the external forces in the form of a pressure force and a viscous force. So here, on the left-hand side, we have what we call the inertial term. So this one we've been discussing a lot since the beginning of the quartal. This is the inertial term. And this one is important when the Reynolds number, we discussed when the Reynolds number is large. That is essentially to say that the viscous terms are dominant over the viscous term. The viscous term is this one here. This is the viscous term. And sometimes the viscous term can be neglected because the fluid is inviscid, so it has very low viscosity. Sometimes also because the flow is inviscid. So the flow geometry, in the rotational flow, for instance, the flow geometry is such that the Laplacian of u is equal to 0. So when the Reynolds number is large, we say that this is the most important term. Right? And so we crossed out the viscous term. That leads to Euler's equation. And one particular simplified form of Euler's equation which we have discussed and used is the Bernoulli equation. Right? When the inertial term is the only term which is the dominant term, so the most important term, then this is also where we discussed inviscid flows, ideal flows. So we've been mostly considering this term here, dominant over that term. Right? And remember that the pressure always adapts essentially to what is the leading force. Right? Pressure is just whatever always develops in the fluid. If the flow tends to compress or tends to change the volume, say, of that volume of that fluid. So Bernoulli equation, potential flow theory, and so on. Now there are cases when the Reynolds number is really small, right? Or sometimes because of certain geometry, so we'll discuss that starting next week, for unidirectional flows, for instance. Or, so this is a particular geometry. And then there is another particular geometry which makes it almost unidirectional, is the case of thin films, so lubrication theory. In that case, we can completely neglect the inertial term, right? So we put the left-hand side equal to 0, and we're left just with whatever is on the right-hand side, which usually is called the Stokes equation. Now, so this is what we'll discuss starting next week. And then, of course, somewhere in between, you need to take both into account, right? And so let me just rewrite the non-dimensionalization of the Navier-Stokes equation. Right, so when we non-dimensionalize the equations, U is now non-dimensional. The tildes represent non-dimensional equations. We wrote, when we normalized the pressure with a characteristic static pressure, so when the inertial term is dominant, then our Navier-Stokes equation looked like that. And the non-dimensional version looks like the dimensional version, of course, but now we have a 1 over Reynolds number in front of the viscous term. And essentially at this point we said, well, if the Reynolds number is large, then 1 over the Reynolds, if the Reynolds number is large, then 1 over the Reynolds number is really small, and therefore we can cross out the right-hand side. Okay? But the problem is that even, so let me just put that here before we got that. In reality, you know that even for high Reynolds number, you cannot always neglect the effect of viscosity. Right? And we discussed that because in the end we also discussed that viscosity is at the origin of circulation. If you had no circulation, if you had no viscosity, then you would have no circulation. You know, when we discuss lift, for instance, we discussed lift for inviscid flows, but we did mention that the reason why you impose the Cotta condition is because in reality there are effects of viscosity. Right? You do not expect the flow to be able to infinitely move around a sharp edge at the trailing edge. And because there are effects of viscosity, because you know that if you do that, if you sharply turn around the corner, there will be enormous shear. And once there are enormous shear, there will be something for viscosity to act on, even if the viscosity is small. Right? So the Cotta condition is, in a way, a consequence of the fact that there is viscosity, even at high Reynolds number. And any times you will see vorticity in your flow, even if you model the vorticity, the rest of the flow as inviscid, then in a way you're neglecting something which really is physically in your system. Okay, so let me just write that. Remind you that even for high Reynolds, the effect of viscosity cannot be discarded. Right, and here think about the Cotta condition, for instance. Think about an irrotational vortex. Right, and I think for an irrotational vortex, this is the best introduction to a boundary layer, because what you do when you model a vortex with an irrotational vortex is you say, well, the flow everywhere is inviscid, so it's irrotational, but I'm stucking all of the viscosity, all of the vorticity, and therefore all of the effect of viscosity, I'm stucking them at just a single point in the center. Right? When we did not, like a more physical model was the Rankine body, where you did have a finite region core where you had vorticity and therefore, if you want, effect of viscosity. But so when you're doing ideal flow or potential flow, essentially what you do is you just stuck all of the effect of viscosity in regions which have no thickness, either a point or a layer. Right? And those in reality have a certain thickness, and those are called boundary layers. So you'll see it just here. Right? So the main problem with completely neglecting this term, there are a few problems with that. So what we did before is just to completely cross out this term. But first of all, mathematically, we run into a problem, and that is, once we neglect the viscous term, mathematically, we can no longer impose a no-slip boundary condition. But we know that if we were to solve the flow everywhere in principle with CFD or anything, we would have to impose a no-slip boundary condition. Okay, so that's the first problem of completely neglecting this term. So let me write that. So when the Reynolds number is large, we neglected this term. So the viscous term, as of now, we've never really discussed, but the problem is that this is the only term that allows us to impose a no-slip boundary condition. that allows us to impose the no slip. So if you neglect that, you can no longer mathematically impose no slip, which is a problem. So in reality, what happens is that when you write this term, right, think about 1 over Reynolds number. Of course, the Laplacian is a complicated number. If you think about your shear stress, right, that would look something like this. You have a shear stress, right, which will scale like that, 1 over the Reynolds number times your shear stress. So what you really have is that even if the Reynolds number is really small, actually here you have the Laplacian because it's the divergence of the shear. Even if the Reynolds number is really, really large, and 1 over Re therefore is really small, the Laplacian or the second derivative could be large, right? But it could only be large if your characteristic distance for y is really small. Right? You see that? So that's, and this is where the whole idea of a boundary layer comes in. Right? So in reality, really, what if, and I think this is a question which, at some point, there are certain applied mathematicians here, and you're neglecting too many terms, make them uncomfortable, and so this is where you can just connect back everything to reality. Of course, when we say we can neglect this term, what if this term here now is very large, right? So 1 over Reynolds number might be small, but what if this term is really large? So what if this here is large? Because when it's large, then we can no longer neglect it, but it's only going to be large in small layers. Okay, that means when if you're thinking about this term here divided by dy squared, right? This will scale like a u divided by, I'm going to already call it a delta squared. So there will be a characteristic length in the y direction. Only when this characteristic length in the y direction is really small, right, are the gradient is going to be large, and its delta going to be large. And that sort of length scale here, characteristic length scale, is the boundary layer thickness. So this delta here, only large in small layers. So the small delta is the boundary layer thickness. So the effect of viscosity, if the Reynolds number are large, are limited to a boundary, a short layer on top of your no-slip boundary. Okay? Is that discussion clear? This is just to introduce the idea of boundary layers and where is the effect of viscosity going to be important. Okay? So what we'll do now is just discuss a physical scaling for that delta, for that boundary layer thickness. So 2 physical picture and scaling. And so for that, let's just just go back to our flow around an airfoil, because we've seen that a lot in the past week. So let's say this is here, even assume this is a perfect Joukowski profile. Now you know everything about Joukowski profile. And what we've been discussing so far is we have a flow coming in from infinity, right? And we computed the velocity. And at the boundary here, we imposed a no penetration boundary condition. which means that you had a slip velocity, right? Which means that the velocity in tangential direction at the wall was non-zero. But in reality, you do have you have to impose a no-slip boundary condition. So what really happens is that whatever we were doing until last Tuesday is solving what sometimes you call the outer problem. Right? So far away from the boundary, let me just represent it here like that. So this here is going to be my boundary. I'm blowing it up because the real boundary there is not that big. Right? But everywhere here, you can still solve the flow, assuming that here, you can safely assume that you can neglect viscosity. That viscosity is negligible. But then inside of this layer, let me actually represent this layer in blue, you cannot. And so when you look at the velocity profile, what you'll see is that outside your boundary layer, you would have the velocity predicted by potential flow theory, for instance. And inside, you're going to have something like that, where your velocity profile eventually goes to zero. Okay? That here will be delta, and this is the boundary layer thickness. So even now, I don't think this is, maybe it's still the case. Like when I was a student, that was definitely the case, but now, of course, computers are more powerful. But what you used to do when you were solving the flow around an airplane, for instance, is that outside you solve for potential flows, and then so you were solving in all of this region, in the outer region here, you were solving assuming you could neglect the effect of viscosity, and then you would match your solution with a boundary layer solver, right, where inside of the boundary layer here, you solved another set of equation where you did include the effect of viscosity. But even physically, this is still, it's still very relevant. So you can still think about everything you did. Right? You don't have to throw out everything we did. Everything we did at this point is still valid in the outer region. You can safely assume the flow is indeed irrotational, and use tools from ideal flows or from potential flow theory. But then what happens is that in the layer very close to the boundary, your velocity quickly drops to zero to match your velocity in tangential direction, I should say, quickly drops to zero to match the no-slip boundary condition. And that thickness is the boundary layer. Okay, so this is essentially what the picture you should have when you think about a boundary layer. And now we'll see how small is small. So how small is this boundary layer? So we'll discuss the scaling for the boundary layer thickness. And so for this, we'll go back to the vorticity equation, and I will discuss a 2D planar case. Okay, so we'll discuss a 2D planar flow above a flat plate. So let's assume that we have a flow at infinity, and here, starting at this point here, we have a flat plate. Okay, so we only start imposing the boundary, the no-slip boundary condition at this point, because before there is no boundary. Now let me put in the corner, if you remember our equation for vorticity, the vorticity satisfies in that case an advection diffusion equation, and we only have vorticity in the z direction. Sorry. So you can think about the vorticity as just a scalar. And so vorticity transports as a passive tracer. And so this term means that vorticity is advected. And that term means here that vorticity is diffused. Now, if you remember what we discussed also when we discussed Kelvin circulation theorem, or that is that if there is no vorticity at infinity, if there is no vorticity here, right, coming in from vorticity, and if initially there is no vorticity anywhere in the bulk here, then there is also no vorticity created. There is no source term, so there is no vorticity created in the bulk of the flow. The only way you could get vorticity at that point, for instance, is if the only place where vorticity is created is at the wall, is where you impose a no-slip. So the only place where vorticity is created is here. So the no-slip boundary condition creates vorticity. Right? The fact that you have viscosity, this is what creates the vorticity. So the rotationality in the flow is due to that no-slip boundary condition. And the no-slip boundary condition is the only place, the boundary is the only place where vorticity is created. So the only way you're going to get some vorticity here, so that you're going to get some irrotationality into your flow, is either two mechanisms. The first one is diffusion. So let me represent that like this. Well, it's not really diffused from inside. This is a bad example because you're going to think that this is like temperature. It looks like temperature. I mean, actually, it's going to be transported exactly like if this plate was hot and you were thinking about temperature. This is what's happening to vorticity. Maybe this is a good analogy. So here at the wall, vorticity is created and it diffuses in the bulk. Right? And it diffuses with a diffusivity constant, which is the kinematic viscosity. The kinematic viscosity has units of meters squared per second, so it's a diffusion constant. So here we have vorticity diffusion. The vorticity diffusion with a diffusion constant equal to the kinematic viscosity. So the kinematic viscosity here is the diffusion constant. And just like for what you've seen in your I'm sure you've seen in your heat transfer class, if that was temperature, it could, there are two modes of transport. It could diffuse, but it can also be advected because you have a background flow. So you also have the fact that vorticity is advected. Let me represent that with a blue arrow. So now the boundary layer, essentially you can think of it as the layer where there is rotationality or there is vorticity in the flow. If there is no rotationality in the flow, then you can assume the flow to be irrotational. You can do everything we did before. So how thick is this layer? Well, you can guess. When you are at the beginning of the plate, the flow is advected, so your boundary layer thickness is 0. And then a certain amount of vorticity diffuses into the bulk and then is swept downstream by the background flow. So if you think about the scaling for that boundary layer, what you expect is something like that, right? And so we'll just do this analysis. So if you think about delta as the length, so let me do this in red because then we'll just discuss diffusion. So the length, vorticity has diffused into the bulk. And so delta is, say, the length scale. For diffusion of vorticity in the bulk, delta scales with the square root of the diffusion constant times time. And so that's the typical scaling for a diffusive length. And now if you want to know what the boundary layer thickness is, right, then you want to think like how long has vorticity, how long could vorticity diffuse here? For how long is it allowed to diffuse and to still affect that region? Right? And that is the time scale for which it takes for flow to go from here to here. Right? If you want the vorticity which you will find at this limit is the vorticity you created here. Right? So you created a vorticity here and then it was swept here over time, which corresponds to, like this, in this case, the ballistic time scale, which corresponds to u infinity times t. Right? That would be the length scale. This length scale here. If you think about this length scale here, now let's write this in numbers. So if now I'm looking at really the diffusive length scale, the boundary layer thickness, we have to think about the boundary layer thickness at a particular location. Right, so what is my boundary layer thickness here at x? So this is the length scale I'm going to try to estimate. Right? So where do I find this? Where do I find vorticity or irrotationality? Over which distance do I find irrotationality? Well, at delta x, it's going to be a diffusive length scale. And for how long could vorticity diffuse in the y direction? Well, that's for the time it took to go from here to here. Right, so you're going to have a square root of mu, right? And t here is going to scale as, let me write here, so t will scale as x divided by u. I put a u infinity, let me just put u here. Yeah? Because x, well, you can just say that x is scaling with u times t. Right? So then you have square root of mu times x divided by u. And this is your typical scaling for the boundary layer thickness. Okay, at a position x. So this is where this square root like shape comes from. Right? So this here, this curve, you can think of this as a square root of mu x divided by u. So the boundary layer, the thickness of the boundary layer grows with x. Right? This is what you get from there. Now, if that scaling argument is still mysterious to you, just really think about the transport. Right? If you want to, and just think about like what needs to happen for vorticity to reach this point. And a simple way of thinking about this is that the vorticity that reaches this point, so you have vorticity constantly diffusing from here, right? The vorticity which is created at the point x is going to diffuse, but then is going to be swept downstream. Right? So the vorticity which is here at any time t was not created at this location. Right? It was probably created early on. So just think about the vorticity created here. It diffuses slowly. Right? It diffuses at a distance which squared with the square root of mu times t, how long it's been able to diffuse. So to get vorticity here, right, that's probably the vorticity which was created at the very tip, the first vorticity which was created, right? And that was allowed to diffuse for the longest time until you reach the time x. Now what is this time? It's the time for which the vorticity is going to be advected downstream, and that time scale is, given that the velocity is u, this is now a advective transport, that time scale is x divided by u. Right? So just, if it's still unclear, just go, just listen to it again until it just permeates. Okay, so now assume that we have a plate of length L, assuming a plate of length L, or for instance, that could be also just be the chord length of your airfoil, or an airfoil of chord length L, right? Then the typical boundary layer thickness will be the square root of mu L divided by U. If you want that, that would be the scale for your boundary layer. The boundary layer at the end of the plate, if you want. And since this is not a non-dimensional number, it is dimensional, you will non-dimensionalize. What will you non-dimensionalize delta with? The only length scale which you have available, which is L. Right? So you make the boundary layer thickness non-dimensional by dividing by L, in which case you get the square root of mu divided by UL. And what do you recognize here? Maybe you do, maybe you don't. Let me just rewrite it in a way that is more familiar. So remember, the kinematic viscosity is the dynamic viscosity divided by the density. So this is, so maybe this you do recognize. And that is the inverse of the square root of the Reynolds number. So that is the typical length, the typical scaling for your boundary layer thickness. Okay. And that is just physical scaling, yeah? This is not, it doesn't tell you anything about really what the flow is, but physically this is how you expect your boundary layer to scale. So let's take an example, just to put numbers in that. Right, so let's think about like a wing, and the chord length is 5 meters. And the what did I put here? The velocity is 100 meters per second. 100 meters per second seems like very fast. If it's an airplane, maybe this is reasonable. I'll just put that down. If someone tell me how many kilometers an hour this is? No, I'm just, 360. So this is okay. No, you're right. So this is fine. Sorry about this. I'm a bit tired. Okay, so then the Reynolds number is, so this is a typical airplane. The Reynolds number when it's landing, the Reynolds number then is going to be 100 divided by 5 times 10 to the minus 5. This is the kinematic viscosity of air. And so you get a number which is on the order of 5 to the 10 to the 7. And therefore you have a boundary layer thickness. Right, so delta, your boundary layer thickness, non-dimensionalized, is going to scale with the square root of 1 divided by 5 times 10 to the 7, which is roughly 10 to the minus 4. Right, so in dimensional terms, that simply means that your boundary layer thickness from the scaling is expected to be 5 meters times 10 to the minus 4. So this is on the order of a millimeter. Okay. So your boundary layer thickness is small, right? That's essentially just the point of that. Yeah, this is 5 meters. So you have 5 to the 10 to the minus 4. You know, it's roughly a millimeter, half a millimeter. It is small. All right. And now comes the heavier part of the lecture. Do you have any questions about, at this point it's been very qualitative. Do you have any question on that? Right. So if you want to think about the boundary layer, this is the place, and you think about vorticity, this is the place where both modes of transport, diffusion and advection, play a role. Right? And the boundary layer thickness, the boundary layer is the only place where you will find vorticity generated at the wall. And therefore, this is the only place where, assuming the flow is irrotational, is not valid. Okay? So this is where you have to look at if you want to get to viscous stresses. But if you also want to, when you wonder, now where is the vorticity? When we were looking at an irrotational vortex, where is the vorticity? Well, it's actually in those kind of small boundaries. Right? So that's what a boundary layer is. And now we will derive the boundary layer equations. And we'll derive the boundary layers by non-dimensionalizing the momentum equation. Of course, you can always solve the fall of the Navier-Stokes equation. Right? You can always do that, but again, those are difficult equations to solve. So what we will do is we will simplify the Navier-Stokes equation to be valid in that boundary layer region. Right? So in that boundary layer region, what we know is that the length scale in the x direction, well, it could be anything. It is 0 from L, it's the length scale of the plate. But the length scale of the y direction is roughly delta. Okay? And when we assume that, then the equations, they simplify to a certain extent, which allows you to actually solve them analytically, well, numerically, but it still simplifies them. So this is what we're doing. So it's not a different equation, it's not a Stokes equation. You could retain all of the terms you wanted, but they become very complicated to solve. And so what we'll do is we'll just rewrite Navier-Stokes equation and we'll just put ourselves in that small layers. And the only thing which we have to worry about are the typical scales for u, v, the velocity u in the y direction, and the length scale in the x, and the length scale in the y direction. So when we non-dimensionalize x, right, the location in the x direction inside of a boundary layer will non-dimensionalize with the characteristic length scale of the plate. So this is going to be L, right? Because x could vary from the leading edge to the trailing edge. But when we non-dimensionalize y, right, we'll only want to stay in a region where there will be rotationality, where there will be vorticity. So therefore, y is going to scale with delta. Okay? So y is going to be delta tilde. Now remember that delta is L times delta bar, right? So really this is L divided by the square root of the Reynolds number times y tilde. So this here, I'm putting this scale. So, you remember where the scaling is coming from, right? This is the scale we just derived. Let's see. Previous paragraph. Now u, the velocity in the x direction. So we are doing 2D planar flows again. The velocity in the x direction is going to scale with the velocity at infinity. So this is going to be u infinity. And what about v? At this point, I'm going to say we don't know exactly how v is going to scale. It's going to be small. We know it's going to be small, but at the same time, the layer over which we look is going to be small. So it's a bit premature to assume anything. So at this point, we'll just give it a scale v, which is undetermined. Right? At this point, this here is undetermined. And we'll scale the pressure because we put the effects of inertia. We'll scale the pressure with an inertial pressure. So with rho u squared. Okay. So those are all of the non-dimensional parameters. I forgot to write that, so what we are doing. what we do here is we just non-dimensionalize Navier-Stokes equation. Navier-Stokes equation in the boundary layer. And so we'll start with the continuity equation, and the first thing, starting with the continuity equation, this is a generic thing now. You'll see we'll do the exact same thing for lubrication theory, because actually the scale, and maybe this is not too surprising, but the scale for V is going to be set by mass conservation. Right? You know that if you look at the equation for continuity in 2D, it's partial U over partial X, partial V over partial Y. This is just another way of saying that mass is conserved. Whatever change in velocity in the x direction you have creates a change, like a mass, an additional or not enough mass that needs to leak then through the other direction, right? So the continuity equation, when we non-dimensionalize the continuity equation, even before we do it, what you expect is that it's going to give you the scale for V. And you'll see that again, I think, in 2 weeks when we'll do lubrication theory. So let's start with the continuity equation. This is partial U over partial X plus partial V over partial Y equals to 0. Right? Just to remind you of that. So when you non-dimensionalize it, I'm going to have a capital U coming out of this U, and I'm going to have an L coming out of here, and a V coming out of this, and a delta, or an L divided by square root of Reynolds number coming out of here. So I'll just write it directly. You have U divided by L, partial U over partial X, plus V divided by L divided by the square root of the Reynolds number, partial V, partial Y. And this is equal to 0. So from there you can deduce a scaling. If this is to be equal to 0, then those two terms, the derivative in the x direction and the derivative in the y direction, they need to be on the same order. Otherwise they can't cancel. Otherwise it cannot be equal to 0. And therefore you get a scaling that U divided by L has to scale with V divided by L divided by the square root of your Reynolds number. And therefore you directly get a scaling for V, which will scale with U divided by the square root of your Reynolds number. So you expect V to be small. So now you have your scale for V, and with that scale you can non-dimensionalize the momentum equation. Okay, so here is a scale for V. And now we'll do the x and the y momentum equation. And we'll take it term by term, and I'm assuming a steady state. Okay, so we'll assume a steady state. We assume the flow has been flowing on top of this airfoil for long enough that we can safely assume that it's no longer changing in time. So the first term in my Navier-Stokes equation is this. Now I'll do it really quickly, but the scale which comes out is U squared divided by L, plus, this is my advection term, I have V partial U partial Y. And so here you have, and there's a row. So I have a row times V times U. So this is going to give me a U squared divided by square root of Reynolds number. And then I have a 1 over delta, and this 1 over delta is going to give me another L divided by Reynolds number, by the square root of the Reynolds number. Okay? So here, this guy here is essentially u. This is rho, my scale for u, my scale for v, divided by delta. And this is rho u squared divided by L. And then I have plus, now equals to minus gradient of pressure, and this gradient of pressure is going to give me my pressure scale divided by the characteristic length scale. Sorry, this is not the gradient. You should have stopped me. This is partial over partial x. Right? So this gives me my scale for pressure, which is rho u squared, divided by my scale for x, which is L. So it gives me minus rho u squared L. Then I have plus. I'm going to have the term which is the second derivative of u divided by x. So this term here is going to give me a mu u divided by L squared. And then the last term, those are all non-dimensional, and then the last terms is going to have to do with the, so it's still in my, so here this is the Laplacian of u, so you have the second derivative with respect to x and the second derivative with respect to y. So you have mu, and the scale for the velocity in the x direction, divided by delta squared, and delta squared is L squared divided by the square root of the Reynolds number squared, which is the Reynolds number. Okay, you can take your break, and while you take your break, I'll finish writing all of this because it takes a long time to write. Okay, so I'll see you back in at 1:45.